Well, so Nicholas might have went a little bit long, but he also provided a very good overview. And this talk is going to zoom in a little bit on an administration workflow problem that we identified in the Coral system for our Summit and Sierra. And in Nicholas's closing arguments, he mentioned the software requirements to get those APIs in common so that players could participate um, and come into standard interfaces to be able to take their innovations and make a direct impact. That's This is one example of doing that and going through the process using OpenBMC. We're going to talk about telemetry because it's very exciting to get a new system every 3 to 5 years, but it when you invest your time as a HPC administrator into being able to give the statistics and and refine your control systems, uh, a new system, while exciting, doesn't it's not exciting to retool all of your hardware or codes to manage the new control systems. And it's not exciting to wake up in the middle of the night to realize there's a proprietary version of the code that has a problem, and you want to go in and affect a change or try something else so that you can get a control pump back online and get some sleep before you solve the problem for real the next morning, right? So um, the let me advance one slide here. So this talk is going to cover that scenario where what do you how can you make it easier and using OpenBMC here to serve telemetry and control system data out of an HPC cluster. Um, OpenBMC is a kind of a partner or maybe a sibling to the Open Compute effort, and from time to time we see server group track discussions about OpenBMC, and historically this OCP committee has fed back into the OpenBMC team some of the changes or at least the needs of the HPC community, and which in terms of telemetry are actually in HPC are more aggressive than standard data centers. From having applied this system to both the IBM cloud and to the Coral system, so we got to see firsthand the difference demand between the two application requirements, and largely in the biggest the HPC, the high performance requirements were more telemetry more often, and then the reliability concerns and the sometimes the longevity. Reliability over time concerns with the novel technology that the HPC community adopts make telemetry, of more of an interest, both because, hey, they might not, these centers may not get a grant, when they expected it, and their hardware needs to live, 1 to 2 years longer than they originally planned, because, or they were waiting on innovations and end up in this timetable, or for any or any other set of circumstances. But it is they're dealing with new innovations, and they're dealing with potentially those innovations over a longer period of time. Those things drive different telemetry needs. So the scope of this talk is going to be about a control system we put in place for Summit and Sierra. Under that Coral contract for those computers, we were asked to adhere and comply and motivate open standards. And so working with the OpenBMC team and contributing to that effort to support that machine was one of the ways we did that. And then the control system that we worked with Oak Ridge to bridge, we made sure that those pieces went into the open community too. So I'll identify those pieces, talk to that experience, and then architecturally there are a few things that are different with this approach than previously. We're going to talk about the out-of-band experience. That's where you're looking at processor controls not going through the OS. So you're doing this without taking CPU cycles. That path provides the less risk to jitter than going through the operating system and hitting the LM sensor path, which already has a standard API. So it's while it's very it's very necessary, it's not necessarily it wasn't innovative per se. So this topic will stray from there. They got to open standards a lot faster than this Outofband thing. But what's enabled here is bringing OpenBMC as an open firmware. All of a sudden you have the ability to do more things with APIs. Their adoption of the REST API and the discovery properties of that API really do change things. And one of the things that changes is we could put an architecture together that was a push-only architecture. So, in that you don't need to send event and telemetry information unless something has changed that you want to hear about. This is an interesting concept because you go from a polling infrastructure where you can look at things every minute, every couple of seconds, or what have you. And if one of those polls fails, then you have an unreliable network. If you go to the push methodology, you can do things much more efficiency and your network load goes down, but then you introduce the complication of, well, how do I know what I don't know? If I have a network failure, what do I do about, all of a sudden you just don't see a push event for a while. So we had to work through that problem. To give you just a little bit more refined view of in-path versus out-of-path, the material in red is the in-path, basically going to the host OS from a aggregator source. In this case, the aggregator is the laptop. And the supercomputer node is the block diagram. But the red path is, again, Linux standard, goes through the Linux Foundation to describe what is in the LM sensor interface. It's a very fast, and you can, because of the, you're using the supercomputer basically in the operating system to monitor these things, you have some very powerful instruments to take cycles from to get the data that you're interested to, draw pretty graphs about power usage and performance. So that's one path. And then the out-of-band path here is defined by the blue. We're grabbing things from an internal component to the CPU called the OCC. And that component is sending information up through the BMC, the controller, the management controller, and on the management network, not on the data network, but on the management network, this comes through up into the aggregator device, the laptop in this case. And here, this was traditionally, this space was dominated by IPMI. I mean, that's been we call it a standard, but the standard is something like 180 pages now. And every supplier has their own edition of that standard. So it's really outlived its usefulness at this point. And REST API and Redfish are coming in to fix that problem at the industrial level. OpenBMC adopts those. And then it's one thing to have that interface, but then how do you manage that interface? How do you collect all the data? How do you apply? Once you get the data in, there's going to be some data that is a known event that you're not interested in, but and you want to filter those things out. So the IBM CRAS-D layer here allows filtering and policy application. For instance, if I have say I have a bad piece of firmware or have a problem in my system where I know that once a month I get a DIM report that's a bogus report, and you've already figured that effort out. You don't ever want to see it again because you know what it is, and you don't want to spend your whole life reliving the event. You can apply policy filters there to say, okay, one, am I worried about this, and two, how worried am I? Am I worried about this, that I'm not going to push this through the aggregation system and wait for a query? Do I want to send an announcement out to say, hey, this is a critical problem that I'm going to lose data if I don't address? Or is it more of a status reporting thing where preventative maintenance wants to pick it up? Those are the kind of things that happen in the CRAS-D layer, and that layer is available on GitHub. So the architecture we came up with, is represented here. Oak Ridge's contribution is really from the the interface between the OpenBMC or OBMC monitor and to the Kafka data stream broker. So Oak Ridge really invented the stuff on the right-hand side of the diagram, and that's based off of their requirements, and they had 4 or 5 different teams that study this data, on these computer systems, and so they have a lot of legacy infrastructure there that they needed to get this data into. And then the stuff we had done from OpenBMC through IBM CRASD is stuff that was generated in the open from IBM to support the system. And so you can see the aggregation from 288 push streams into IBM CRASD into the monitor, and where there are 16 monitor nodes that then fed into Apache Krafta and then off to disk. Historically, the effort was to go from the left-hand side to the right-hand side as quick as possible and get the data onto persistent store. The scalability of the system and and some of the other design parameters for the control systems said that we might not want to wait for an event to go all the way through there. If there's a critical event that implies that a control system's not pumping water into a liquid-cooled rack, I want to know about that before somebody runs a standard query from the data at rest. I want to know about that while the data is in flight. And so we considered the architecture to have this, in the service node to process active in-flight data ahead of them getting into the data broker stream. And of course, you're not trying to hide anything but there's definitely data that you do not need to have coming into your disks and wasting space. And so that there's a discussion to be had there, and there were decisions made along the way for what data wants to go to disk, and then what data on its way to disk wants to be identified for more use. So so of course the question is well, how good is this architecture? How do you test it? And so we took some measurements along the way and published some of the results from the system under load, doing different things. And we have different events here between the event genesis all the way through the what's needed to get across the management networks efficiently, where the service nodes will actually compress and push up to Kafka, and then ultimately before it gets to disk, decompression happens on systems that are up separate from the HPC cluster. And so some of the data here, I think is interesting. Yeah.
Sorry to interject, but we're kind of at the time limit.
Okay.
So I
give
don't
me
know
30 seconds.
Yep, go for it.
All right. So what was interesting here is the latency information coming through, where we could process these number of events from all of the 4,000 plus nodes in the tune of 2 to 3 seconds per within a very high scale of observations. The consistency, the second diagram shows you how consistent that data was, and the outliers there are representative of the network conditions that you wanted to know about, but weren't sure that you were going to get without having a pull framework. So it's a bit of a characterization step to say, hey, if I haven't heard from a node in 6 seconds, I might want to address what's going on there if I don't have an event that says that node's down. And then lastly, there was a question of how stale is the data? By the time I look at it and I want to do a query on the data, what's the staleness from the event generation? And that's represented in the third graph. And so that's basically saying that every 4 seconds you can get, from this prolifera of over 100 and some events per node, you can get that data out to the system that's queryable. And interestingly enough, when we looked at this from a data center perspective, they said, well, can you give us, an event set once every minute? And we said, well, we can do it every 4 seconds. So, it just kind of goes to show you the difference in demand between the HPC world and the data center world.
Okay, Steve, I think we're going to have to stop you.
All right.
But Thanks.
So if you want to know more, join Alan's project and we can talk about it more.
Great. Thanks, Steve. Much appreciated. Very good.